I'm Matteo Farina, and in this video I will present our CVPR 2023 work, Quantum Multimodal Fitting. On the one hand, in this work we introduce QMF. QMF starts from the notion of preference matrix and follows the steps to solve problems with AQCs. In the first step, a logical graph is obtained with a QUBO formulation. In the second step, the logical graph is mapped to the QPU topology by means of a procedure called minor embedding. In the final step, the AQC undergoes an annealing process, terminating in a state that represents the retrieved solution. On the other hand, we introduce DeQuMF. DeQuMF partitions a multimodal fitting problem into equally sized independent subproblems and iteratively uses quantum retrieved information to shrink the search space. Multimodal fitting deals with fitting multiple parametric models to a set of noisy and outlier corrupted observations in order to provide an optimal explanation to the data. However, since multiple explanations are possible, the problem has an inherent combinatorial trait. To overcome this, we propose QMF, the first quantum algorithm to solve multimodal fitting problems. However, the current generation of adiabatic quantum computers has limited resources. Therefore, it cannot properly scale to real-world problems. To this aim, we propose DeQuMF, an extension to QMF that enables AQCs to solve real-world problems. Let's break the mathematical formulation of QMF down. QMF starts from the notion of preference matrix, a binary matrix whose columns are the model's consensus sets. From a mathematical perspective, it has this formulation. Visually, instead, it looks like this. A preference matrix has as many columns as the number of sampled models, and has many rows as the number of sample points. Building on this notion, we can formulate multimodal fitting problems in the disjoint set cover formulation. In this formulation, we seek the smallest subset of disjoint models that explain all the available observations. Under these terms, we assume a simplified scenario where no outliers are present in the data. We can reformulate the disjoint set cover minimization to its soft version by relaxing the constraint with a multiplier denoted by lambda. Then, we reorganize the formulation to a QUBO, having both a quadratic and a linear term in the binary unknown z. The QUBO represents the same objective as the initial disjoint set cover, but it is feasible for quantum annealers. Experimental results show that QMF can solve with misclassification error equal to 0 multimodal fitting problems until faulty models are sampled. From that point on, due to the current immaturity of quantum hardware realizations, performances start dropping almost exponentially. Moreover, the amount of physical qubits involved in minor embedding grows superlinearly with the sample hypothesis. Both of these observations lead us to conclude that a decomposition would be beneficial. DeQuMF arises from these needs. It works by first partitioning the preference matrix into multiple, equally sized partitions. Each partition size allows for reliable solving with QMF. Subproblems are independently solved with QMF in order to obtain local binary assignments. Using these assignments from QMF, we can shrink the search space until it meets a desirable size to then solve it further with QMF and obtain the final solution. DeQuMF proves very effective when tackling real-world size problems, as depicted by this plot on synthetic data. Moreover, the soundness of the decomposition policy is confirmed by the results, where execution on quantum hardware significantly outperforms execution on classical hardware with no decomposition. Decomposition proves effective also on classical hardware, with state-of-the-art comparable results. DeQuMF displays state-of-the-art comparable behaviors also on well-established benchmarks, the Adelaide RMF dataset, top left, the York and the Hopkins benchmarks, bottom right. Our decomposition policy also enables us to use real quantum hardware on real-world sized datasets. These visualizations, in fact, are qualitative results obtained with DeQuMF on the D-Wave Advantage 4.1. Finally, we test our method on a scenario falling out of its design, single model fitting with outliers. In this setup, our method displays more robustness to an increasing outlier ratio than the previous single model fitting state-of-the-art method in the quantum literature for adiabatic quantum computers. In summary, we brought a new, very important problem into AQC admissible form, and we introduce a decomposition policy that enables AQCs to scale to real-world size multimodal fitting problems. Notably, our decomposition policy proved to be more robust than the previous quantum state-of-the-art on single model fitting, although designed for multimodal fitting. I sincerely hope that this presentation was interesting and helpful. Thank you for your attention.